Hello, hello. I'm going to talk about Gauss's law with two of our favorite charged three-dimensional shapes, spheres and cylinders. We will start off with a sphere of uniform charge density. So it's got a volume density, total charge over total volume is that expression right there. That is all well and good. When we are using Gauss's law, we're usually trying to determine the electric field at a certain point. So we will start by doing the electric field outside of a charged sphere. So the electric field is pointing radially outwards if this thing is positively charged. When we make our Gaussian surface, it's kind of like making a balloon go like around the object. You can pick whatever shape balloon that you want, but you want to pick a balloon so that the surface of the balloon is equidistant to the surface of the object, so that the electric field lines will poke through the balloon at a right angle. But a mathematician will say that the electric field lines are parallel to the area vector. Okay, so if your surface is the same distance at all points from the object, then your electric field should be constant if it's at that right angle. You can just pull the electric field out of this integral, which makes things really nice. This is like the primary advantage of Gauss's law. And so then we're left with like this surface area integral of this closed surface, which isn't really calculus. This is consult the formula chart for the surface area of a sphere, which is 4 pi r squared. Okay, so notice that for this sphere, I do use little r. So little r, like the Gaussian surface isn't anything physical. It isn't anything like real. It's not tangible, right? It's this imaginary balloon that we've blown. By inflating or deflating this Gaussian surface, we can find the electric field at any distance from our actual physical object, which is kind of represented on the right side of this equation. Okay, remember that Gauss's law is equal to the electric flux. Okay, the electric flux is like the number of field lines that like passes through a surface, and that's only determined by the amount of charge that is contained within the surface. So, that being said, this becomes really easy. It becomes really familiar. Gauss's law usually uses the electrical permittivity constant epsilon naught, but a lot of times we use like the constant K, the Coulomb's constant K, because it's a lot shorter to write. But these two electric field equations are equivalent. So that's easy. Okay, a little bit more difficult is dealing with, what happens if we want to know the electric field within this insulating sphere? Maybe we like dig a tiny little hole and we like burrow in to this insulator, and we want to know how much electric field there is at each point. The left side of the equation is exactly the same. Okay, your Gaussian surface is now just inside the object, but since your Gaussian surface, it's like your imaginary balloon anyway, like that's fine. The tricky part here is actually finding Q enclosed. Okay, with a uniform charge density, we can make a ratio between like the total charge and the charge that is enclosed. Okay, depending on how the question is phrased, you might be asked to find Q enclosed in terms of the charge density rho, or you might be asked to find Q enclosed in terms of like the total charge. Okay, so whichever one is appropriate, you solve it for Q enclosed, and then you pop that in to your Gauss's law equation. So I chose to do this in terms of total charge. I came up with this expression right here. Okay. And I want you to take a look at the equation we got for the electric field outside and inside. Okay, the variable that we would be changing would be little r. Okay, so when we're outside, we have an inverse square relationship between electric field and like distance away from the center of the charge. But when we're inside that conductor, we've got a direct relationship. Okay, and so our electric field versus radius graph looks something like this, which, thinking back to like our gravitation unit, this looks exactly the same as a gravitational field as you like tunnel through the center of a planet. So just, again, another similarity between electric fields and gravitational fields. There is something kind of quirky about electric fields. We don't have to use an insulator, right? We could have a conducting sphere, but unlike an insulator, if we've got charge on a conducting sphere, that charge is going to repel like other like charges. Those excess charges are going to move to the surface of the sphere. It's going to become uniformly distributed on the surface, but nothing's going to be on the inside. So within any conductor, the electric field is always going to be 0. And then on the outside of the conductor, it's just going to be normal. It's just going to be kq over r squared. Okay, so that's a quirk with a conductor. So the conductor would have just like a flat line from 0 to capital R, right, the radius of the object, and then it would jump up. There would be like a discontinuity, and it would be inverse square for the rest of it. So we like spheres for Gauss's law. We also really like cylinders. I would say that these are probably the only two shapes that you would be asked to actually like calculate anything with Gauss's law. The simplest form is if we had like a uniform line of charge. So it's like you have a wire, it's got charge on it. That charge is going to be evenly distributed because that's what charges do when they're on like a wire. Here, the appropriate Gaussian shape would be like another tube. It would be a cylinder, right? Because your cylinder, it's going to be, the same distance from the wire the whole entire time. And the field lines that are coming from the wire are going to poke through the surface at right angles, or again, as your math teacher would say, those electric field lines would be parallel to the area vector of that cylinder. We are ignoring the ends, like the right side and the left side of the cylinder. We're going to say like a negligible amount of flux goes through those ends. And so we're just really focused on what's coming through like the side here. So, again, the left-hand side of the Gauss's law equation, it looks like a scary integral, but it's really like, can you find what the area of this can, right, the side of the can is? So 2 pi r, right, the circumference of the circle, multiplied by the length, it's going to give you the area of that side. It's a little bit annoying. We got to use the charge density to figure out the charge that's enclosed. If you're given total charge, I mean, that's easy, right? Just use Q. But for your cylinders, because they're usually long, a lot of times for these, you'll be asked to do this in terms of charge density. So in this case, we've got charge density lambda. And so the charge that is enclosed is going to be equal to lambda times L. Okay, and so the L on the left side of the equation, the L on the right side of the equation are the same. So they cancel out, you rearrange, you solve, you get this nifty little inverse relationship. So the farther you move away from this wire, your electric field is going to decrease, not as an inverse square like the cylinder, but just as a plain inverse. Okay, easy peasy. This is slightly more difficult. If we were to have like a thick wire, one where like, they're going to give you like the charge density, like the volume charge density, that again becomes a little bit more annoying. Okay, the left side of this equation is going to be exactly the same as that of the wire. I can work a little bit harder on the right side. So there's my expression for volume there on the bottom, right? I'm going to take the surface area of the end, right? And if I multiplied that area by length, that's going to get me volume. Okay, so a couple of notes here now that we're looking at this whole thing. I like to think of the left side especially. The left side is all imaginary. It's your Gaussian surface. It's this imaginary balloon that you're inflating to whichever level that you need, right? So that like the surface of that balloon is at the radius that you're trying to find the electric field at. Wow, that was a long sentence. The right-hand side of this equation, it deals much more with your physical object. Okay, so take a look at those notes there. Your physical charge only exists to big R, right? Whereas our Gaussian surface, little r, is like larger than that. And then, as I mentioned before, like, if we're going to ignore the flux through the ends, your length has to be relatively long. When you're working with a cylinder, the length always needs to cancel out. So, like, just do it. It's fine. So that's what's going on there. We can rearrange, solve for the electric field. Okay, we get an inverse relationship. Okay, just like we did with the line of charge. And so, I mean, that kind of makes sense. Because your solid cylinder is just a scaled up version of your line of charge. Yeah, okay, wow. I totally just, let that play. The inside of the cylinder, it's a little bit more complicated, right? Finding Q enclosed on the inside, you have to set up like your volume ratio. Okay, so I kind of did that earlier, right? You can see where I took that and I plugged it in. A lot more stuff cancels out this time. And we get a direct relationship here between electric field and the radius, like the distance away from like the center of the wire. Okay, surprisingly similar to the sphere, but it makes sense. Okay, the more charge that is enclosed, like the bigger the electric field will be. So sure, that's fine. Nothing wrong with that. I'm just trying to think about like all the different ways you might be presented this. Instead of a volume density, you might be given like a linear density. You might be like, every slice of this like solid cylinder has like a certain like surface area charge associated with it. So there's a slick little conversion that you can do here. Okay. So volume density is charge over volume. Volume for this particular case, right? It's going to be the cross-sectional area multiplied by the length of the cylinder. Oh, hey, earlier we said that charge over length, that's linear charge density. So you could say that rho is equal to your linear charge density divided by your cross-sectional area. So I just thought this was kind of cool. When you pop that in to the electric field formula we found for like the outside of the solid cylinder, and you can do this for the inside as well. I just didn't want to make this take too terribly long. When you do that, you can see that the electric field for the solid cylinder simplifies to the same electric field as that is surrounding a long piece of wire. I just thought it was neat. That is all I have to say about Gauss's law and spheres and cylinders for today.